When a chemical reaction reaches equilibrium, there's going to be a certain amount of products and reactants present. Depending upon what the value of K sub C is, we can tell if it's really big that it would be a product favored equilibrium, or if it's really small it would be a reactant favored equilibrium. Somewhere in the middle there's usually about an equal amount of reactants and products present. There are some things that we can do though in order to alter or adjust the composition of the equilibrium mixture or change the amount of reactants relative to products once that system reaches an equilibrium state. So some of the things that we can do are add a reactant or a product, remove a reactant or a product, adjust the pressure or the volume. This is in particular for reactions involving gases. And we can increase or decrease the temperature of the reaction. So we could heat it up or we could put it on ice and cool it down. These are all things that we can consider when adjusting the composition of an equilibrium mixture. Changing these factors is often referred to as Le Chatelier's principle. Le Chatelier's principle says that if a stress is applied to a system, the system will react in such a way to overcome that stress. Those previous four factors that we talked about are stresses. Our system would be the chemical reaction. So if we add something, remove something, change pressure or volume, add heat, remove heat, however we stress our reaction, the reaction will overcome that in such a way. And however it overcomes it will determine if it adjusts by making more reactants or if it adjusts by making more products. And this is how we alter that position of chemical equilibrium. So the first two were adding or removing reactants or products. If we add a reactant or a product to our chemical reaction, the system will shift away from that addition. Essentially, we will have added extra of something and it will want to react it away and use it up. And so it'll use it up by making more product or more reactant, opposite of whatever was added. So it shifts away from that direction of the addition. On the other hand, if we remove a reactant or a product, now the system realizes something's missing. So it will shift towards that removal and it will replenish what was removed. So it shifts towards what's taken away and it shifts away from what was added. If we have the reaction nitrogen plus hydrogen forming ammonia, what direction will the equilibrium shift if the following are changed? If we add more nitrogen to our system. So imagine we're at some equilibrium currently, and in our equilibrium mixture we have nitrogen, hydrogen, and ammonia present, all three of them in some ratio. And now we're going to spike the system. We're going to add more nitrogen to it. So if we increase the amount of nitrogen in our system, now we have added a reactant in this case, and there's extra nitrogen lying around. The system will react in such a way to overcome that stress of having extra nitrogen, so it reacts it away. That added nitrogen will now combine with the hydrogen and it'll shift away from the addition towards the products to use it up. So it'll end up creating more ammonia, more NH3. So in this case, we would say that the reaction will shift to the right, or you might say shift towards the products. Whether you say right or you say products, that means the same thing. Now, what direction will the equilibrium shift if instead we remove H2? So now in this case, we're taking away a reactant. So if we reduce the amount of hydrogen present, maybe we siphon it off in some way, now our system realizes that it's lacking hydrogen. So it needs to overcome that stress of having less hydrogen by generating more. So the equilibrium will shift towards the removal, or to the left, or the reactants in this case. It shifts towards whatever you take away. So to overcome that loss of hydrogen, the equilibrium will shift left, or shift towards the reactants. Whenever we take something away or we add something, that system will attain a new state of equilibrium. The equilibrium will be different than the initial equilibrium because in the first one where we added more nitrogen, our new equilibrium composition will contain more ammonia and less nitrogen and hydrogen, but it'll eventually reach a new state of equilibrium. In our second one where we removed the hydrogen, now at equilibrium, there's going to be more nitrogen and hydrogen present and less ammonia because our overall system shifted to the left after that removal. For the reaction of carbon monoxide plus water forming CO2 plus H2, predict the direction, either to the left or the reactant side, or the right, the product side. The equilibrium will shift from the following changes. Adding carbon monoxide, so adding CO to our system. If we spike the reaction with some carbon monoxide, the system wants to overcome that addition by using up the excess carbon monoxide, so it'll shift away from the addition, in this case, to the product side. So we're going to shift to the products, which also could be said shift to the right. If we add carbon dioxide, add CO2, now we're adding a product to our equilibrium, but we still are going to have excess, and so the reaction will want to use up that excess carbon dioxide, and so it'll do that by shifting to the left or the reactant side. So it shifts away from that addition. So in this case, we would shift towards the reactants and make more carbon monoxide and water. Removing H2O. If we remove our water, which is a reactant, we take it away. Now the system realizes that it's lacking something, and so it will overcome that stress essentially by generating more of it, what you took away. So it'll shift towards that removal or towards the reactants to the left. Or if we remove CO2, if we remove some carbon dioxide, the system will overcome that stress by creating more of it, and so it'll establish equilibrium again by reshifting to the right and generating more carbon dioxide and hydrogen. So in this case, it will shift to the products, or in other words, to the right-hand side. When we're dealing with reactions involving gases, we could also adjust the pressure or the volume. Volume and pressure are inversely proportional to one another. If you remember from Boyle's law, P1V1 equals P2V2, there was an inverse relationship between them. So if you increase the pressure of your system, by default that means you would be decreasing the volume. Or if you increase the volume of your system, that would mean that you're decreasing the pressure. And the only things that really change when we adjust the pressure or volume is where the gases go. So we have to have a system involving gases in order for pressure or volume changes to really do anything at all. Imagine that this is a chemical reaction, or our system, and it's inside of a chamber that will tell us the pressure. So there's 9 particles in here, so we can imagine that there's 9 moles of gas. And in that first example, the piston is pushing down fairly far. So it's at a relatively low volume. And if those gas particles are pressed together in a low volume, they're going to be having collisions with one another and with the walls of the container very frequently. And those collisions were the pressure that we measured when we were talking about gases. So when you have a gas confined to a small volume or a low volume, that's going to correspond to a high pressure. And now if we lift that piston up and we have those same 9 moles of gas, but now they're at a higher volume, they're going to still be able to have collisions and generate a pressure of their own, but the collisions with the walls of the container and with each other are going to be less frequent. So the pressure will decrease. The bigger space that that gas has to expand out in, therefore it will have a lower pressure that it will exhibit. So this shows that inverse relationship between volume and pressure. When dealing with a reaction involving gases, if we increase the pressure of the system or decrease the volume, those two mean the same thing, the system will shift to the side with the lesser number of moles of gas. Essentially, you are increasing that pressure and the system wants to alleviate that pressure somehow. So the number of moles of gas present must decrease in order to alleviate that extra increased pressure. So that's why it'll shift to the side with the lesser number of moles of gas to help get rid of that excess pressure that you imposed on the system. So on our reactant side, we have 1 mole of nitrogen gas and 4 moles of hydrogen gas, 3 moles of hydrogen gas. So we have a total of 4 moles of gaseous reactants. And on our product side, we have 2 moles of ammonia, so we have 2 moles of gaseous products. So if we were to increase the pressure or decrease the volume, the system will overcome with that extra pressure by shifting, in this case, to the right-hand side or the product side, because there's a lesser number of moles of gas on that side, only 2 moles of ammonia. So in this case, we would shift to the right. On the other hand, if we decrease the pressure of a system or increase the volume that gas can be in, by decreasing the pressure, we're alleviating the strain from the pressure of those gases. So the number of moles of gas can increase. The system will shift to the side with the greater number of moles of gas if you decrease the pressure on them. So we had 4 moles on the left of gas and 2 moles on the right. If we decrease the pressure, the system will overcome that stress by shifting to the left-hand side where there's more moles of gas. If you have a reaction that has no moles of gas of reactants or products, so essentially 0 moles, or if you determine that the moles of gas are the same on the left-hand side and the right-hand side, then the position of equilibrium would be unaffected by changing the volume or the pressure, since pure solids and liquids and aqueous solutions are essentially unaffected by changes in pressure or volume. Do the products increase, decrease, or remain the same when the following reactions experience a decrease in pressure? If we have a decrease in the pressure of the system, that would mean we have an increase in the volume. So essentially our reaction containing our gases could be present in a bigger vessel, a vessel that contains more space. So by putting our reaction in a larger vessel at a lower pressure, we're alleviating some of the strain from the pressure of those gases themselves. In this case, we have PCl5 in equilibrium with PCl3 and Cl2. We have 1 mole of gas on the reactant side. We have a total of 2 moles of gas on the product side. If we decrease that pressure, we're going to allow the system to shift to the side with the greater number of moles of gas. So in this case, our reaction will overcome that change, that stress, by shifting towards the PCl3 and the Cl2, or towards our products. So do the products increase, decrease, or they remain the same? In this case, the products will increase. When we have a decrease in pressure. For our bottom reaction, we have 3 iron, which is a solid, plus 4H2O, gaseous water, in equilibrium with iron oxide, solid, plus 4 moles of hydrogen gas. So on the left-hand side, there's 4 moles of gas, just looking at the gaseous water. And on the right-hand side, there's also 4 moles of gas, the gaseous hydrogen. So if our system experiences a decrease in pressure, since the number of moles of gas on the reactant side and the product side are identical, there will essentially be no change. There'll be no shift because they're both the same. For the reaction of solid calcium oxide plus carbon dioxide gas forming solid calcium carbonate, what direction will the reaction shift when it experiences an increase in pressure? So remember, if we increase the pressure, we're decreasing the volume that the container's in. Those two mean the same thing. So we could think about taking our system, our reaction, and placing it into a smaller vessel where now it has less space, and so therefore the pressure inside would increase. And we're creating that strain on there, and so our system wants to react in such a way to alleviate that additional pressure. And it can do that by lessening the amount of gases present at equilibrium. So on our reactant side, we have 1 mole of gas, the CO2, and on our product side, we just have calcium carbonate, which is a solid. So we have 0 moles of gas. So in this case, when you increase the pressure, it's going to shift to the right-hand side towards the calcium carbonate and try to get rid of some of that CO2 present because that is creating pressure itself and we've increased the pressure on the system. So it wants to get rid of some of that excess by shifting to the side with the lesser number of moles of gas. So in this case, we would say the reaction would shift to the right, or in other words, towards the products when we have an increase in pressure. The next type of stress that we could impose on our system is either increasing or decreasing the temperature of the reaction. All of our other previous stresses, such as adjusting amounts of reactants or products, changing the pressure or volume, they do not adjust the value of Kc. The value of Kc is constant as long as the reaction remains at constant temperature. But a change in temperature will change the value of the equilibrium constant. How the system adjusts to either an increase or decrease in reaction temperature will largely depend upon if the reaction is an exothermic reaction or an endothermic reaction. For an exothermic reaction, such as nitrogen plus hydrogen forming ammonia, the enthalpy of reaction is negative. That means the reaction releases heat when it goes from reactants to products. The graph on the right shows the equilibrium constant K on the y-axis versus temperature on the x-axis. We can see that the temperature increases, causing a decrease in the equilibrium constant. A large equilibrium constant means that a reaction is product favored, whereas a small equilibrium constant means that a reaction is reactant favored. So as we are increasing the temperature of the reaction, the value for K is going down, it's decreasing. So it's becoming more reactant favored or less product favored as the temperature increases. So for an exothermic reaction, K sub C is large at lower temperatures. So exothermic reactions must favor product formation at low temps. K sub C is small, or it's a reactant favored equilibrium when the temperature is high. So in that case, if we heat up a reaction that's exothermic and put it at high temperatures, we're definitely not going to favor product formation. We'll shift back in the direction of our reactants. For an exothermic reaction, the delta H of the reaction is equal to a negative value. And what that means is that heat is a product of this reaction. So it's easiest to think about it if we just throw heat into our overall chemical equation. For an exothermic reaction, we would write heat on the product side because going from reactants to products, heat is being released when the enthalpy of the reaction is negative. If we increase the temperature of an exothermic reaction, we're doing the opposite of what that reaction wants to do. An exothermic reaction wants to give off heat, and we're putting kinetic energy back in the form of heat. So we can think of the heat as if it's just like any other species in our chemical reaction. If we're increasing the temperature or adding kinetic energy in the form of heat, we're going to shift away from that addition, and we're going to shift towards the reactants of an exothermic reaction. Or you can think about it like you're doing the exact opposite of what it wants to do, so you're going to shift away from that addition of heat. So in this case, we would shift towards the reactants or make more nitrogen and hydrogen at equilibrium when we heat up this reaction. Versus if we cool it down. So it's exothermic, so the heat would still be a product. But if we cool it down, we can think about it like we're taking away heat. We're removing kinetic energy. And we learned that when we remove something, we shift towards that removal. So cooling down an exothermic reaction is helping it out. You're helping the reaction give off heat from the system, which is the reaction, to the surroundings. So in this case, it'll shift towards that removal or towards the products. So in this case, we went towards the reactants when we added heat, and we went towards the products when we removed heat. And this is true for any exothermic reaction. Now imagine we have an endothermic reaction, one where the enthalpy of the reaction, or delta H, is a positive value. N2O4 forming 2NO2. For an endothermic reaction, the value of the equilibrium constant increases with increasing temperature. So if we were to graph this, it would look something like this. Temperature on the x-axis, our value of our equilibrium constant on the y-axis. And we would see that our trend is that as we increase the temperature, K sub C starts to go up. So at low temperatures down here, we have low values of K sub C. That's where our reactants are favored. And at high temperatures, we have high values of our equilibrium constant, which is where our products are favored. So if we have our reaction and it's endothermic, we can plug heat in as a species, and that would end up going on the reactant side for an endothermic reaction because heat needs to be absorbed for an endothermic reaction to progress. So it's a reactant. And if we increase the temperature of an endothermic reaction, we increase the heat, we're adding it in, it wants heat to go forward, it needs it, we're helping the reaction, and we're going to shift away from our addition. And so in this case, we would shift towards the products. If we decrease the temperature of an endothermic reaction, so add heat to our reactant side, and now imagine you take your flask and you set it on some ice, you cool it down. You're doing the opposite of what that reaction needs. An endothermic reaction needs that energy to progress forward. That's the definition. And so now you're essentially removing that heat, and you're going to shift towards that removal or back towards the reactants. So for an endothermic reaction, adding energy in the form of heat or increasing the temperature of a reaction is favored, and it'll help you shift towards your products. If you cool down the reaction or decrease the temperature, you're going to shift towards that removal and back towards your reactants. Recall that in our chapter over kinetics, we briefly talked about catalysts. A catalyst is something that will help increase the rate of the reaction. It'll speed it up, but it will not be consumed itself, so it's not actually part of the chemical reaction. It would be regenerated with the products as it was with the reactants. A catalyst worked by creating a new pathway for the reaction. So if this is our activation energy, or our E sub A for our uncatalyzed reaction, the catalyzed reaction would have a much lower activation energy. So it interacts with the transition state, or the maximum on the potential energy diagram, and it allows the reactants to clear that maximum state easier by lowering that activation energy. The reactants are still at the same final energy as the products. That did not change with the catalyst, but what it did was shrink that height of our overall E sub A. The catalyst has no effect on the equilibrium composition. It only makes the reaction go faster. So overall, if we add a catalyst, how would it affect the equilibrium concentration is that it would have no change. It doesn't alter the amount of reactants or products present at equilibrium, just gets us from point A to point B quicker. Let's try a couple examples putting everything together. For the reaction, nitrogen gas plus oxygen gas forming 2 nitrogen monoxide gas. Delta H for the reaction is positive 186 kilojoules. How does the amount of NO present vary with the following changes? So now we're saying, how does the amount of nitrogen monoxide present at equilibrium go up, go down, or not change when we do all the following? We impose these stresses on our system. So if we increase the temperature, for this reaction, we saw that delta H was positive, so we had an endothermic reaction. If it's endothermic, we can think of the heat as being a reactant. And if we increase the temperature of our reaction, in this case, we add energy in the form of heat, we're going to shift away from our addition, away from the heat that we added. So we will shift towards the products. And NO is our product. So we're saying, how does the amount of NO adjust? In this case, we're shifting towards the product. So we're going to make more nitrogen monoxide. So the NO will increase at equilibrium, that new equilibrium that's established after. If we add oxygen, if we add O2, adding something, in this case, the system knows that there's extra of it and it wants to use up that extra, so it overcomes that stress by shifting away from the addition. In this case, we'll shift to the right or towards the products. So at equilibrium, the amount of nitrogen monoxide will increase. If we remove N2 gas, take away a reactant, now the system overcomes that stress by making more of what was taken away and shifting towards that removal. So it's going to go back to the left, away from the nitrogen monoxide. So if we remove N2, the amount of nitrogen monoxide will decrease. Decreasing the volume, which is another way of saying increasing the pressure. And we learned that we had to determine first the number of moles on the reactant side that was a gas and the number of moles on the product side that was a gas. So in this scenario, we have 1 mole of N2, 1 mole of O2, so a total of 2 moles of gas on the reactant side. And then we have 2 NO, so we also have 2 moles of gas on the product side. So in this situation, since the moles of gas are equal to one another, changing the pressure or the volume will not do anything. In this case, there would be no change. And lastly, adding a catalyst. Adding a catalyst does not affect the position of equilibrium, just the rate of the reaction. So adding a catalyst also will have no change on the amount of NO present at equilibrium. Here we have the reaction, 2O3 gas, which is ozone, forming 3O2 gas, which is oxygen. Delta H for the reaction is negative 285 kilojoules. How will the equilibrium shift? Left, right, or no change with the following. So in this case, since we have a negative delta H, this is an exothermic reaction. And if we increase the temperature, we want to first plug in that the heat is essentially a product of an exothermic reaction. Heat's normally given off. So in this case, if we increase the temperature, when the reaction's trying to give off heat, we're doing the opposite of what it wants to do. We're going to shift away from that addition back towards the reactants. So adding heat to an exothermic reaction will cause it to shift to the left. Adding O2, if we add oxygen, which is a product in this one, we're going to shift away and use up that excess oxygen and form more O3, which is ozone. So we'll shift to the left. If we remove O3, take it away, reduce the amount of ozone present, the equilibrium will adjust and replenish what was lost, so it'll shift towards the removal. So we'll shift towards the ozone, which is to the left, or the reactant side. If we increase the volume, or in other words, decrease the pressure, at a lower pressure, we're going to allow the reaction to have less stress from the gases that are present. So at a decreased pressure, we can shift to the side with the greater number moles of gas. On our reactant side, we have 2O3, so 2 moles of ozone, and they're gaseous. And on the right-hand side, we have 3O2, so 3 moles of oxygen gas. And at a decreased pressure or increased volume, we'll end up shifting towards the side with the greater number of moles, which in this case is the product side. So we'll shift to the right. Lastly, decreasing the temperature of an exothermic reaction. We can still plug in our heat as a product. In this case, we would be removing heat. So our exothermic reaction will adjust by shifting towards that removal. So that would be like putting the reaction on ice. And we'll shift towards the O2 production or to the right-hand side.